Welcome back to our discussion of limits. Last time, we talked somewhat extensively about this graphed function that had all of these jumps and holes and things filled into it, and no function you're going to encounter in the wild is going to look this weird. The functions you're going to encounter in the wild are going to look like, well, functions that you're used to. So in this video, I want to talk about when limits are useful for algebraic functions. That is, functions that you're actually likely to encounter. So the thing I'll say is, most of the interesting limits of algebraic functions, that is, functions that are just written out with x's and such, they almost always come from fractions that if you just plugged in the number, you'd get 0 over 0. Now, I'm not changing the rules here of 0 over 0. 0 over 0, like any division by 0, is undefined. It's, in some sense, nonsensical. But if you compare 0 over 0 to something like 12 over 0, this is nonsense. This is much worse nonsense. This is basically unsalvageable. If you get something where it wants to be 12 over 0, nothing nice is going to happen. But often, things that have a 0 over 0 in them, often those end up being salvageable by using limits. So I wanted to talk about some of the basic things that can come up. So I'm going to do a bunch of variations of limits real quick, where we go through the various combinations, 0 over 0, some number over 0, some 0 over some number. We'll talk about all the sorts of combinations of zeros and not zeros that can come up in fractions. So to start with, let's look at the limit as x goes to 2 of 2x minus 6 divided by x squared minus 16. What this is asking me is if I plugged in a number really close to 2, like 1.99 or 2.003, in for x, what would this be really close to? And the best way to think about any time fractions come up is to separate what happens to the numerator and what happens to the denominator. So if x is close to 2, then what is 2x minus 6 close to? Well, it's going to be close to minus 2, because 2 times 2 minus 6 is minus 2. And if that x was a little bigger, I'd get a number that's a little bigger than minus 2. If that x was a little smaller, I'd get a number that was a little smaller than minus 2. But whatever happens, a little bigger, a little smaller, it's still going to be close to minus 2. Likewise, this denominator is going to end up close to minus 12. Again, if x is close to 2, then x squared minus 16 is going to be close to minus 12. If x is a little bigger, then again, this would be a little bigger than minus 12. If x is a little smaller, it would be a little smaller than minus 12, but it's still going to be really close to minus 12. And so what that tells me is if I plug in a number that's really close to 2, I end up with something that's really close to minus 2 divided by something that's really close to minus 12. And so then this ends up being minus 2 over minus 12, which is 1/6. Now, if what you're thinking is, hey, if my function had literally been this, all we did was spend a really long time calculating f of 2, you're totally right. That's exactly what happened. We spent a long time calculating f of 2 in exactly the same way we would have in the previous chapter. When something like this comes up, that's when you have a graph that looks something like this. No ugly breaks or holes or anything like that. And you're looking at the limit as x goes to 2. And the graph is just perfectly reasonable. And so if you plugged in 2, you'd get this number. If you plugged in numbers near 2, you'd end up getting numbers that are close to this number. So, in other words, limits in this example bought us nothing new. Okay, let's take the same thing, 2x minus 6 over x squared minus 16. And let's look at what happens as I take the limit as x goes to 3. Okay. Again, I need to pay attention to what happens to the numerator and denominator separately. The numerator here is going to end up close to 0. Okay. Again, the key thing here is if x is a little bigger or a little less than 3, this is going to end up being a little bigger than 0 or a little less than 0, but it's still going to be close to 0. And this denominator here, it's going to end up being close to minus 7. And so when I go to plug in a number really close to 3 to this fraction, I'm going to end up with something really close to 0 divided by something really close to minus 7. And what's that going to be? Well, if you take something really tiny and you divide it by minus 7, it's still going to be tiny, still going to be close to 0. So this limit is 0. Okay. Now, you'll recall it is zeros in the numerator and denominator that we need to specifically pay attention to. But if I only have a 0 in the numerator, but not in the denominator, then the limit is just 0. In terms of the graph, again, nothing special here actually happened, other than that at this particular point, my graph of whatever sort it looked like crossed the x-axis because the value was 0. Okay. Nothing too weird. So those are the two benign cases. The two benign cases, again, are the case where neither the numerator nor the denominator is something near 0, in which case you just plug it in, and the case where the numerator is 0 but the denominator isn't, in which case you just get 0, and you don't even have to think about it anymore. Okay, so let's look at now the limit as x goes to 4 of yet again the same thing, 2x minus 6 divided by x squared minus 16. Okay, here the numerator is going to 2, and the denominator is going to 0. So here, what's happening, I have some number that's definitely not 0, and I'm trying to divide it by 0. Now, thinking back here to what I said before, that's the bad kind of nonsense, where I have a non-zero thing divided by 0. So if the numerator is not going to something that's approximately 0 and the denominator is, then the limit, for now, we're just going to write undefined. Okay. I'll note there is more to say about exactly what kind of undefined it is. And so what does the picture here look like? The picture here looks like what happens when you try to divide by 0. Well, math doesn't like it, and so you end up with a graph that sort of spikes off to infinity, and then spikes off to minus infinity in the other direction. Okay? And so you end up with what's called a vertical asymptote. And so really what's happening here is that the function is spiking either off to positive infinity or off to negative infinity. And we'll talk later about how to sort out exactly whether it's spiking off to positive infinity or negative infinity. But for now, for this section, you could just write undefined. Okay, so now, one last example here. I want to see what really happens when we actually have this 0 over 0 case. And so this, again, this is the interesting case. 90+% of the limits that you do are going to end up in this 0 over 0 case. Okay, so I want to see what happens here. And so I'm going to try and factor some stuff. So if I factor the numerator here, I'm going to get 2 times x minus 4 divided by x minus 4 times x plus 4. And everything here hinges on the fact that there's an x minus 4 in both the numerator and the denominator. That's what's making it 0 over 0, in fact, because when x is 4, 4 minus 4 is 0. And so that makes both the numerator and the denominator 0. So what do I want to do? I want to cancel these two. Now, we talked a bit before about how you can kind of cancel them, but you kind of can't cancel them. And here's why. The reason is because if you have 3 over 3, you're allowed to cancel the 3's. If you have 0 over 0, you are emphatically not allowed to cancel the 0's. And so I can only cancel the x minus 4 with the x minus 4 if x minus 4 isn't 0. That is really, to cancel these, we really need x minus 4 to not be 0, which is to say we really need x to not be 4. But, good news. If we go back to the definition of a limit, what does the limit care about? The limit cares about the output that f of x is close to for inputs that are close to, but not equal to c, where this c is the thing I'm going to. So when I'm looking at the limit as x goes to 4, I care about x's that are close to 4, but specifically not equal to 4. And what does that mean? Well, for x's that aren't 4, x minus 4 isn't 0, and so I can cancel it. And so I will get the limit as x goes to 4 of 2 divided by x plus 4. And having done that, I can do my usual thing of saying, okay, well, now as x goes to 4, what's happening? Well, the numerator is going to 2, and the denominator is going to 8. Both of these are not 0. And so, huzzah, this is going to be 2/8, which is 1/4. And that's it. That is how we would do this limit. And so the moral here is that when you actually have a limit that is of the 0 over 0 flavor, what are we looking for? We're looking to do some factoring so we can do some cancellation. And again, I want to emphasize that this exact time, the 0 over 0 flavor, this is what's going to happen 90% of the time you're doing limits. And the reason for that is, well, in the other instances, it either didn't get us anything, or it just acted like evaluating a function. And in neither of those instances did we really gain anything. So the only time that limits are interesting is when they let us do something we otherwise could not do. And that happens to mostly be the 0 over 0 case. So most of the time I ask you a limit question, it's going to end up being something like this, where you're going to have to factor and cancel and do that kind of stuff. This 0 over 0 case warrants a little bit more explanation. First of all, what does the graph look like? Well, the graph in this 0 over 0 business ends up looking like a regular graph, but it's got a hole in it at the input that we're looking for. Okay, and so here we're looking at the input 4. Because of the 0 over 0, the function was undefined at 4, and so the graph of the function ended up having this hole. And what the limit did was the limit allowed us to fill in this hole and evaluate the function there anyway. That's what happened. Next up, I wanted to address why is it that if I divide something that's about 0 by something that's about 0, it doesn't blow up in the same way that we said if you divided something that was about 2 by something that was about 0, it was going to blow up. And here's why. Here's two numbers that are about 0. What's that? Well, that's minus a half. That's plausible. So if you divide two numbers that are close to 0, you could get minus a half. Okay. Just as easily, you could take something like this. These two numbers are close to 0. But if you divide those, it'll be 10. In fact, if you divide two numbers that are close to 0, you could actually get any number. And so because of that, you don't actually know what sort of thing is going to pop out. So when you start doing the limit, and it's of this 0 over 0 flavor, anything could happen. All right, I'll wrap up this video for now. In the next video, we're going to do a bunch more examples of the 0 over 0 flavor of limit, and the sort of algebra and factoring and the sorts of things that come up therein. But that's all for now. I'll see you next time.